The goal of this exercise is to familiarize ourselves with the details of a thermodynamic cycle. So what is a cycle? Well, in words at least, a cycle implies that the system begins and ends in the same state. Now, we've used the word state a few times, and I just want to make it absolutely clear what that refers to. That means that if you measure individual system properties, that the initial system properties must equal the final system properties. So if you pick a property, like density or pressure, whatever you want to choose, some macroscopic property that can be measured, the initial system properties must equal the final system properties. Well, you might look at this and say, that's really boring, a cycle doesn't do anything. As we'll soon see, cycles can do things despite starting and ending at the same place. Let's sketch out a sample cycle on a PV diagram to see what I mean. We'll start by putting down a set of axes, and let's put down our first state, state 1. Well, state 1 has to be connected to state 2 by some process, so we'll pick something that looks like a polytropic process going to state 2. Then we'll go to state 3 this way via what looks like a constant volume process, and we'll end up back at state 1 going through a constant pressure process. So if you see, if we add up processes 1 to 2, 2 to 3, and 3 to 1, we did actually end up back where we started. We're back in state 1 at the end of this cycle. But we've done something, and if you're not convinced, let's look at the work. So I'm going to shade in the work, and I'm going to do this in a way that illustrates what the net work should be. So let's say that all of the parts of this plot that feature positive work, I'll shade with these horizontal lines, and all of the parts that feature negative work, I'll shade with these vertical lines. So the idea is that if we cancel out positive and negative work, you should see a cross-hatching like a tic-tac-toe board. That stuff all goes to 0. The stuff that's left over will be the net work. So to illustrate, where does the positive work come from in this cycle? Well, process 1 to 2 is certainly negative work. You're going to the left on a PV diagram. Process 2 to 3 is vertical. There's no work associated with it, no volume change. The only place you get positive work is the area underneath process 3 to 1. So let's shade that in there. So that's all positive work. But now we also have negative work associated with process 1 to 2. And that'll be, remember, the area underneath process 1 to 2 all the way down to the axis. So all of this gets shaded with vertical lines. Well, as I said, the cross-hatching all cancels out, right? The same amount of positive and negative work are done in that rectangular region. So the only part we have left is in that modified triangle near the top, and that's all negative work. That tells us, regardless of the exact value, that the net work done in this set of processes must be negative. We're going to move that over so that we can use that information later. What I want to do now is to walk back through the steps in our cycle over on the PV diagram while simultaneously illustrating on the right what could be happening with a piston system that we're reasonably sure we can understand. So let me draw in the piston, and the idea is that our system is that green stuff inside the piston cylinder. The piston itself, to the left, will be able to move around to compress or allow the gas to expand, and there are 2 reservoirs, hot and cold, labeled there. Currently, they're not in thermal contact with our system, so nothing happens, but when one of them comes into contact with our system can potentially exchange heat energy with the reservoirs. When I use the term reservoir, what I'm trying to emphasize is an external region that is so extensive, so large, that its temperature won't change appreciably by coming into contact with our system. You could imagine the cold reservoir, for example, being Puget Sound, where if we're attaching this little piston to it and the water is really cold, we're not going to heat up all of Puget Sound just by attaching this little piston to it. Likewise, the hot reservoir could be a giant container of hot water, some big piece of metal that's really hot, whatever you want. One other important detail, though, hot and cold only make sense in reference to one another. So we know that the hot reservoir has a higher temperature than the cold reservoir, but actually the system at various times in its evolution may be hotter than both reservoirs, may be colder than both reservoirs. As we'll see, that will actually enable heat transfer in either direction to either reservoir depending on what else we're doing with the work. So first, let's put state 1 on the PV diagram. Of course, the piston doesn't move for a single state, but in process 1 to 2, now we expect the piston should move because we're going to a smaller volume on the PV diagram. So indeed, as that proceeds, the piston compresses and our system becomes smaller. Now apparently there was no heat exchange involved in that process Neither of the two thermal reservoirs came into contact with our piston. But now we're going to execute process 2 to 3 to get down to state 3 at constant volume. You can imagine if you don't change the volume and you are changing the pressure, you probably are going to have some heat exchange. So let's see what happens. So going down to state 3, we come into contact with the hot reservoir, and those arrows point up from the piston to the reservoir. That tells us that heat was actually exchanged from our piston system to the hot reservoir. Again, that may seem weird. Why would we exchange energy with the hot reservoir when it would be easier to do so with the cold reservoir? Well, actually, in this case, we can imagine that the piston system was so hot that we were still able to efficiently transfer thermal energy to the hot reservoir. As we'll see, part of the idea behind this entire cycle is that we can do that. Alright, finally we're going to execute process 3 to 1, going back to where we started in the cycle. So let's do that and see what happens with our piston system. So the cold reservoir comes into contact and the piston expands. So you could see that we actually had heat energy transfer from the cold reservoir to the piston while simultaneously expanding out the piston's volume. Now it may seem like these heat exchanges are somewhat arbitrary, but actually we know something very precise about the net amount of heat that has been exchanged as a result of this cycle. Let's move the piston over just so we have a little more room, and write down the first law of thermodynamics, conservation of energy. So the change in total energy on the left-hand side must be Q minus W, and I'm going to do something that may seem controversial. I'm going to cancel out the change in kinetic energy, the change in potential energy, and the change in internal energy. How can I get away with that? Well, if we're considering the entire cycle, we know that the initial system properties are equal to the final system properties. That tells us, since all of the energies are constructed from macroscopic measurables, namely properties, that actually there must be no net change in kinetic energy, no net change in potential energy, and no net change in internal energy. The whole left-hand side of this is 0. That sets up a very simple relationship between Q and W, namely that they're equal to one another. So W cycle must be Q cycle. They must be equal to one another. So if we know that the net work is negative, as we decided from the PV diagram a long time ago, that tells us that the net heat transfer must also be negative. Now, if you remember what both of those mean from the conservation of energy expression, when the net work is negative, that means that work is being done on the system's energy increases. When net heat transfer is negative, that means that energy is taken away from the system through heat transfer. So all of the energy we added to the system through work ends up escaping through heat transfer. And we know the directions of heat transfer because we drew those little arrows on the hot and cold reservoirs. Now, rather than drawing a piston every single time we have a cycle like this, more often than not we draw out a schematic version of a cycle that looks something more like this. So this is intended to represent the cycle that we just saw sketched out on the PV diagram. All of the arrows indicate the direction of energy transfer. So Q in, that's heat transfer from the cold reservoir into the system. Q out, that's heat transfer out of the system into the hot reservoir. And W cycle indicates that the environment did work on our system. So you can think of the system as being that rectangle with the circle inside. The circle is just to remind you that it is a cycle, so it begins and ends in the same place. Now you may think, what a wacky thermodynamic cycle, how would we ever use something like this? Purely speculative. Well, what if we miniaturize this and put it on top of a well-insulated box? Well, you can probably see where I'm going. We've made the cold reservoir into that insulated box, and if we open it up, sure enough, it's a refrigeration system. So the idea is that the reservoir is actually what you're trying to keep cold. The system itself is the motor attached to your refrigerator. The hot reservoir is, in most cases, the rest of your kitchen. Now you could make this into an air conditioner where the hot reservoir is outside. You could also have a very similar cycle that works as a heat pump, and we'll talk about those a little more in class. But for this particular application, the idea is that we wanted to keep our ice cream cone freezer cold, and we did that by constantly removing energy from it every time we executed this cycle. The source of the work in this case? Well, you have to plug your refrigerator in. Otherwise, eventually, you'll get equilibrium between the refrigerator temperature and the ambient temperature, the temperature of your kitchen, and at that point all the ice cream melts. A sad day for everyone.